Okay. Thank you, sir. Now we have Dr. Arvind Krishna Sai Baba, who will speak on randomized algorithms for tensor decomposition. Dr. Arvind is an associate professor of mathematics at North Carolina State University. He got his master's and PhD from the Institute of Computational and Mathematical Engineering at Stanford University. Before that, he studied at the National Institute of Technology, Karnataka, where he obtained a BTech in Chemical Engineering in 2007. His research interests are numerical linear algebra, inverse problems, and imaging, and uncertainty quantification with applications to biomedical imaging and environmental. Thank you.
All right. Can you hear and see? Can you hear me and can you see my slides? Okay.
Yeah, we are able
Okay.
to see.
All right. Thank you so much for the introduction and the invitation to give a talk here. So I'm going to talk about randomized algorithms for tensor decompositions, and this is joint work with my former PhD student Rachel Minster and my former postdoc advisor Misha Kilmer. So just to motivate my talk, we've talked about matrices quite a bit. So why tensors? So from my perspective, there are two main motivations for it. So one is, data and more generally problems in scientific computing are fundamentally multidimensional in nature. So for example, if you take a single image, as Siva mentioned, you can think about it as a single matrix. If you think about a series of images, even about the same person, so for example, a video, that would be a series of images would be a tensor. And then if you add more features, like you take many people, or if you take in color, you already see there are 5 dimensions in place. And very often, numerical methods tend to process them using matrices rather than tensors, because that's what we're used to, because algorithms for matrices have been so powerful that it's sort of second nature to process them in the matrix. But what we lose when we do things like that is we lose the multidimensional nature. So we want a tool that's able to exploit the multidimensional structure. So tensors, as I'll talk about, naturally allow for this to happen. So I'm going to talk about a particular flavor of tensors known as the Tucker format. And when it comes to tensors, there are about 7 or 8 different types of ways of thinking about it. So it's very confusing and very hard to get into it because of it. But I'll talk about one, which in my mind is very natural. But it's also great because it's a very good choice for compressing data. So that'll be a focus of my talk. And if you start with this format, you can convert to another format. So that's once you have a good approximation in this format, you can use it as an initial guess for other decompositions. Okay, so here's a more of real life example. This was done by people in the national labs here, so at Sandia. And what they were interested in is, the national labs simulate really complicated partial differential equations. So for example, let's say they do a 3D domain. I think this particular example, they were doing a combustion problem in which they're solving a problem over 3 dimensions, 1 temporal dimension, so that's 4 dimensions already, and they were tracking about 64 variables, so a lot of species, chemical species. So that's 3 plus 1 plus 1, so that's 5-dimensional problem once again, and it yields 1 terabyte of data. Maybe 8 terabytes is not too bad these days, but you have to run it hundreds of times over different configurations. So the amount of data that you can generate is just balloons. But when ultimately, what do you want out of this data? You want to answer scientific questions. So if you spend half your time just loading up the data, you can't answer these questions. So you want to load them very efficiently, just as you would load a PDF on your computer or something. So what they did was they used tensor decomposition because it's a 5-dimensional data set rather than unfold it to make it one large matrix. They use tensor decompositions, and they compress it. And here's what they observed. So on the x-axis is the error due to the compression, and this is the compression ratio. So when you want very good error, so the order of 10 to the power of -6, the amount of compression that you get is very small. So you get only 5x compression, or that means you have reduced it from 8 terabytes to 8/5. But if you can tolerate a little bit of sloppiness, so you increase the error here, you can get incredible compression. So at 10 to the power of -2, you get about 5,000 x compression. So that's, you're storing it in probably gigabytes instead of terabytes. This is just one data set. If you look at this other paper here, I was just looking at it yesterday. They were achieving compression ratios of about 200,000. So the potential, what I'm trying to say is that there's a lot of potential for compression. And if you can tolerate a little bit of error, from a visual perspective, 10 to the power of -2, you can hardly tell the difference. So I also want to highlight this paper to show you that there's a lot of work on high performance computing. So this paper here did tensor compressions on hundreds of cores. So I don't work on high performance computing, but I know there's a workshop on high performance computing. So I want to point out that there are a lot of opportunities for new algorithms for tensors and new even software implementations for tensors. It's a very new and exciting field. Some of the fundamental developments in this area happened only like 10 or 15 years ago. So if you're just getting started on your PhD or getting started on your career, this is a great area to be in. So with that, I want to bring up the outline of my talk. I'll try to keep it more of a tutorial nature. Unfortunately, anything to do with tensors is a little bit technical, so bear with me a little bit. So I'm going to start talking about matrices and talk about compression in matrices, and an algorithm that I've worked on a lot is randomized SVD. I'll talk about that a little bit. I'll talk about tensors, one particular flavor of tensors. There's a lot more. There's a whole zoo of tensors. And time permitting, I'll talk a little bit about my work on tensors. Okay, so let's start with SVD. Hopefully all of you know this, but if not, this is a very quick recap of it. So the singular value decomposition, Siva talked about the successes of the 20th century, and one of them was the decompositional approach. And the crown jewel of the decompositions for matrices is known as singular value decomposition. So if you're given a rectangular matrix, it decomposes it into the product of 3 matrices, 2 of which are orthogonal. So that's nice matrices to work with. So U and V are orthogonal. They're on the sides. And you have a diagonal matrix sigma. And these diagonal matrices have non-negative entries. And you can arrange them in decreasing order like this. So the number of non-zero singular values is actually the rank of the matrix. So already that tells you something special about the matrix. So I'm going to highlight these quantities in red because they'll be what are known as the dominant matrices. Because there's an ordering of the singular value. Sometimes the first few singular values are very large and the rest of them are small. And that's what we'll see in many situations. So that's one way of writing it, writing as a product of 3 matrices. You can also write them as a sum of outer products. So these terms are kind of order 1 quantities. The magnitude of these quantities is controlled by the sigma j. Again, a few of them are large and others are small. You can truncate them. So that's kind of a nice idea. So how is this useful? So let's take a simple image. I got this from one of the Python toolboxes. This is a raccoon. This is an image of size 700 by 1000. And if you plot the singular values, the sigma j's, I'm plotting this on a semi-log scale. So you see that this is the index of the singular value, and this is the magnitude of the singular value. You see that the first few ones kind of dominate. So within the first 20 indices, it already decreases by 2 orders of magnitude. And even further, singular values decay quite a bit. Now, there's nothing special about this image. It's sort of true of most images. So this tells you that I can sort of cut off the singular values here. And throw away the singular values. By throwing away the singular values, I'm compressing the matrix. So I can store it more efficiently. So that's the main idea behind image compression. Now that's not how the JPEG format and other compression formats work, but they work on very similar ideas. In fact, you can show that by truncating the small singular values, the matrix that you get is the best low rank approximation of that rank. It's a very famous theorem known as Eckert-Young. So what happens when you actually do this in practice? So let's say instead of keeping all the singular values, you keep the first R singular values. And then I vary R. So this is 25, 50, 75, and 100. I reform the matrix and see what happens. So for target rank 25, it's not a great quality image, but you can still make out the raccoon. So if you're only interested in identifying the object, that's pretty good enough, right? So if you increase the rank, slowly the image quality improves. And at rank 100, if I superpose it with the true image, you can hardly tell the difference, right? But already by rank 100 instead of rank 700 or rank 1000, you've achieved like 1/5 compression. So that's how it works for matrices. Again, there's nothing special about this image. You can go ahead and try it with any other image. This works. So with 3 lines of code, you have a compression technique. Okay, so problem is matrices tend to be very large, especially data sets that we work with these days. You run with like gigabytes and terabytes of data. So you can't just apply off-the-shelf techniques like singular value decomposition. So the technique that I like to use in certain situations is known as a randomized SVD. And I learned about it when I was in grad school, and I still think it's one of the coolest things I know. Okay, so let's say you want to compute a rank R SVD approximation. It's a numerical method that's an approximation of. So what you do is you pick you let R be the target rank, and you denote P as oversampling parameter. Think of oversampling parameter as 5 or 10, something that's fixed and constant. What you do is you draw a random matrix that's Gaussian. That means entries are normal 0, 1, mean 0, and variance 1. And they have to be independent. So this is a tall and skinny matrix. This is my matrix A. This is omega, which is n. This is R plus P by n. Those are the dimensions relative to A. Then what you do is you form this matrix vector product A times omega. Okay, so this is where all the magic happens. And in red, I'm denoting all the quantities that are random. So I'm continuing to propagate the random quantities. So A times omega, what it does, it basically mixes the columns of A. Okay, so randomly mixes the columns of A. So that's what matrix vector multiplication does. So you get this matrix Y. Some people call it as a sketch. And the beauty about this Y is that if you've chosen the enough number of columns of omega and some other conditions I'll talk about, so then Y, or if you normalize it, so if you compute the thin QR factorization, Q, it forms a very good approximation to the column space of A. So the left singular vectors, if you want to think about it. So then what you can do is you can project the matrix onto this column space. So you compute this low rank approximation QQ transpose A. Now this approximation is good in a sense I will make a little bit precise later, but you get a good approximation to the matrix, and this is a low rank approximation. So that's known as range finding. You want to approximate the range or the column space. Now the second step is to convert it into the SVD format. Actually, all the hard work has been done here. To go from this step to this step, it's a little bit of work and it's technical. I don't want to get too much into it. Basically, you form Q transpose A, you truncate it, you compute an SVD, but it's a much smaller SVD, so it's easier to do. And you compute a low rank approximation of this. So again, the quantities in red are all random. So when analyzing it, it's a little bit hard. Okay, so there are 2 main questions to answer here. Is this computationally efficient? And is this accurate? So I'll answer the first 2 questions. Is this computationally efficient? So if you are looking for a dense matrix, and let's say M equals N, then this is of the order of N cubed. So that means if you double the size of the problem, the cost grows not linearly, not quadratically, but cubically. So it becomes 8 times more expensive. The randomized SVD, as making no other assumptions on the matrix A, if it's dense, then the cost is not cubic anymore, it's quadratic, but it depends on the rank of the matrix, the target rank you are selecting. So it's quadratic up to this R, and if R is much smaller than N, this is more efficient. I see that there's a question. Let me see if I can answer it. Are there any measuring methods to check the quality image based on? Yeah, you can. Yeah, if you have something like a norm, like a 2 norm or a Frobenius norm, you can use that to measure the quality of the approximation. Yeah, like I said, I want it to be tutorial. So if there are more questions, yeah, please feel free to bring it, or we can ask it at the end. So. Okay, so yeah, here's where the quality of the image comes up. So you can, in this case, I'm measuring the error in the Frobenius norm. There's a theorem that guarantees the error. So the best low rank approximation is because of the SVD. It's the singular values that you discard. So sigma j from R plus 1 through Mn. That's the best quality. So whatever approximation you're going to get is worse than that. The question is how much worse? It's worse by a factor of the square root of 1 plus R or P minus 1. So R is the target rank and P is the amount of oversampling parameters. So the more oversampling that you do, the more work it is, but the error is a little bit better. I don't want to spend too much time on the theory, but here's what happens if you try it out. So I'm doing this on 2 different matrices, and this is the best possible error, the one in blue, that's Eckert-Young. I cannot beat this, the Frobenius norm. I cannot beat this with any other matrix of the same rank. Then this is the quantity that I get from the randomized SVD. So you can see that it's pretty good. It's not perfect. You can see that there is a little bit of a gap here, but the error tracks pretty well. And this is the bound. So this is the upper bound that I'm plotting here in black. And this bound is also fairly informative. So what this theorem says, basically, if the singular values are decaying, which is the situation in those image compression methods, the singular values are decaying very rapidly. So the tail of the singular values is small. So then it says that the error is not too bad. It's bad by this factor. It's not too bad.
Red colored line is the expected value. So you're sort of doing it, generating many samples of it, and then finding the error, or what?
No, the bound is in the expectation. This is just one realization of it.
Oh, so even one realization is less than the. Okay, fine.
Yeah, no. The Eckert-Young is the best, right? So you can't beat it. So any realization will be worse off.
The red one.
The red one, yeah, the red one is the realization. One realization.
There's one realization. Okay.
Yeah. Yeah, I'll talk about it in a probabilistic sense in a second. Same with matrix 2. This is a different singular value decomposition. You can see that there's a big gap between 20 and 21, but all three measures track pretty well. The randomized SVD is a little bit worse off than the best case scenario, and the bound is pretty informative here as well. So this is when things work very well. Now you can ask the question, well, what if I'm having a really bad day? I draw a bad omega, what's going to happen? So there are theorems to explain. Actually, yeah, I just want to point out that if you want to get into this area, there's a wonderful article by Halko Martins and Trop. It's a little bit of read. I mean, it's 100 pages long, but and I read it periodically. So I highly recommend you if you want to get into this area. So yeah, like I said, so what if I'm having a bad day? I draw a bad omega. Is it going to be really bad for me? The short answer is no. It actually works with very high probability. And there are theorems to prove this, but I think this plot is more informative. So what I'm doing here is I'm increasing the target rank from 10 to 25, and each time I'm drawing about 1,000. I think it's about 1,000 samples. So I'm drawing 1,000 different random matrices, and I'm computing the error, and I'm keeping the x-axis the same magnitude. So it goes between 0 and 1. Okay, so as the target rank is increasing, what you can see is that the error is shifting slowly to the left, right? So it's shifting a little bit to the left. The mean, but also the variance is shrinking. So you can see that this is wider than this. So as the target rank is increasing, both the mean is decreasing and the variance of the sample variance is also decreasing. So there are theorems to prove this, that to explain this behavior, but that's typically what you see. These algorithms work very well. Like it's very unlikely that you'll draw a really bad omega, and they work with very high probability. The only question is whether your singular value decomposition, the singular values decay well. Once you're in that situation, it works very well. Now, if the singular values don't decay, there are algorithms to fix it, but it's a little bit more expensive. Okay, so that's what I had to say about matrices. So I'll go into tensors, but if there are any quick questions, I can answer it. Right. Okay, like I said, you can always bring it up. And can you let me know how much time I have left? Do I go until 20?
You have about 10 to 10 minutes easily, 10 to 15 minutes.
Okay, maybe I'll speed up then. Okay, so okay, tensors, right?
You can take your own time. 20,
okay.
20 minutes, say maximum.
Okay, thanks. Yeah. Okay, so what's a tensor? The one-dimensional tensor is a vector, and the two-dimensional tensor is a matrix. The third three-dimensional tensor is a cube. Can go into 4 and 5 dimensions easily. Gets harder to draw, but you can still consider it. Okay, so to talk about tensor decompositions, I have to talk about something known as fibers, and then unfolding. So I'll build it gradually. So for matrices, you have rows and columns, just like that. For three-dimensional tensor, you have column fibers, you have row fibers, and you have tubal fibers. So the tubal fibers go into the screen essentially. So using these fibers, you can define what are known as unfoldings or matricization. It's very hard to say it, but that's what it is. So okay. So imagine you had a two-dimensional tensor, a three-dimensional tensor. It's 2 by 2 by 2. You can unfold it in. You can unfold a D mode tensor in D different ways. So a three-dimensional tensor you can unfold in 3 different ways. I mean, you can do it more ways, but these 3 ones are kind of important ones. The first one, first way it takes the columns. So it's 1, 2, 3, 4, and then 5, 6, 7, 8. Right? So that's the first way by arranging the column fibers. Then you can arrange the row fibers. So it's 1, 3, 2, 4. So when you do it, you flip it. So it's 1, 3, 2, 4. And then 5, 7, and 6, 8. So that's the second way. So the second mode unfolding. And the third mode unfolding is you go like this: 1, 5, 3, 7, 2, 6, 4, 8. Okay. So it gives you 3 different matrices. And already you can see that each one of them has a row, its own row and column space. So you have 6 spaces to work with. So in general, you have 2D spaces to work with. So you can already see that tensors are a little bit more powerful than matrices because you have more spaces. So you put the potential for compression in some senses, or even the structure that you have at your disposal is much higher. Then once you can unfold things, you want to multiply tensors with matrices. So let's say you want to multiply a tensor with a matrix. You have to make sure the dimensions are right, and I'll explain how to make sure the dimensions are right in a second. So let's say you want to multiply in the mode J. So if you have a tensor, you can multiply it with a matrix in 3 different ways. So along mode 1 from the left, along mode 2 from the right, and along mode 3 from behind. So for d-dimensional, there are j different ways, and it's denoted as this times j operation. And there's a formula entry-wise, which I can never remember, but you can do it. But the way I remember it is easy. So what you do is, if you want to multiply it in the jth mode, you unfold x in the jth way. So you know how to unfold a matrix. You just unfold it like a deck of cards. You just unfold it, and then you multiply the matrix multiplied by the matrix on the left. Okay, so now you know how to match the dimensions. The number of columns of A has to match the number of rows of xj. So that's why that's the stipulation on these sizes. So that's how I think about matrix tensor multiplication. It's like matrix multiplication if you look at it the right way. Now, using that idea, you can prove things. So you can multiply it in more than one mode. So you can multiply it through modes 1 through k. that's how you do it. You just do it one at a time. And the beauty is that it doesn't matter which order you contracted. You can multiply it, the starting from back to the front or front to the back. It doesn't matter too much. It follows from the associativity of matrix products. Okay, I know there's a lot of notation, but yeah, just bear with me. So finally, we can talk about a decomposition. The decomposition, you take a tensor, let's say a 3D tensor. You can write it as a product of these three things. So this is these are factor matrices Q1, Q2, and Q3. You have D of them for D modes. Then you have something known as a core tensor. So it's you can choose Q1, Q2, Q3 to be orthogonal. So it's looking a little bit like the singular value decomposition. Singular value decomposition is 2 dimensions and you have 2 matrices. Here you have 3 matrices and you have a core tensor. Now the problem is that this core tensor is not diagonal. So, but and not is it non-negative. So you've lost something from dimension 2 to 3. It's no longer like the SVD. In fact, you can show that there is no perfect analogy to SVD in higher dimensions. But anyway, you get a decomposition like this. It doesn't have the nice properties, but you can work with it. So you write it compactly as this core tensor G and this factor matrices. The factor matrices go on the side. G is the core tensor. Okay, so that's known as the Tucker decomposition. Now, if you want to think about what the optimal low rank approximation is, now this is where it starts to be a really hard problem. Now, one thing I forgot to mention is that the rank of this tensor, for a matrix, you had one rank, which is the number of singular values. It's the same as the number of independent rows, independent columns. Now in tensors, depending on the flavor of tensors you use, there's a multi-rank. So with each mode, there's a rank associated with it. And that's basically the rank of the unfolding. So you unfold the matrix in that mode, and then you compute the rank. That's one component of the rank, and you have a tuple like this for the rank. Okay. So now, if you want to find the best rank approximation to a tensor, you can solve this optimization problem. You can show that there is a solution. It exists. That's why I wrote the min here rather than infimum. But you can't compute it so easily. It's not so easy to compute. With SVD, there's a closed form expression for it. It's hard to compute, but there's a closed form expression for it. Unfortunately, there's no closed form expression for this. You have to solve an optimization problem. So yeah, just back to what I was saying, you can solve it analytically for 2 dimensions, but 3 dimensions, you can't solve it analytically. You have to solve an optimization problem. And remember, we're talking about big data problems. Even if you talk about 5 dimensions with 100 in each dimension, that's already 100 to the power 5. That's a really hard problem. So computational cost becomes a big bottleneck. So because of this, people use approximation algorithms. One is called the HUI, high order orthogonal iteration. It's solved by sequence of problems. It unfolds it, solves it, unfolds it, solves it. So that's one way, but it's very expensive. So what people use is known as the sequentially truncated high order SVD. So even the names start to get really complicated. So SVD is, you know what SVD is. High order is for tensors. Sequentially truncated, I'll explain what that is in a second. Okay, so what are the steps here? You want to use matrix methods as much as possible. So what you do, once you get it in a tensor, you unfold it to become a large matrix. It's a short, fat matrix. So you unfold it, you get a short, fat matrix. What you do is you compute an SVD of this, and then you truncate it. Okay, so that's the main idea. You compute this truncated SVD. You split this into 2 parts. The first part is the UR. The second part is the sigma RVR transpose. This part becomes the core tensor, the things that are on the side. And then these 2 parts become the next core tensor. Okay. I know it's a little bit hard to explain, but that's how the algorithm. So you compute the SVD, you take part of it, make it one thing, take the other part and make it another thing. So what you get at the end of it is this kind of approximation. You get a core tensor, and you get these factor matrices, which are the left singular vectors. Okay, so why it's called sequentially truncated is that as you go along, the tensor that you're working with decreases in size. And the first time you work on it, there's nothing you can do other than work with the whole tensor. But once you compress with it a little bit, you work with the compressed tensor. Now you work, let's say you compress along mode 1. Now you compress along mode 2. You chop this off after. And then mode 3, you compress it like this. And then you keep going on. You're working with smaller and smaller chunks of matrices. Okay, you can show that this is the best low rank approximation. This exists. This algorithm doesn't produce the best low rank approximation, so that's why it's an upper bound. But it's a factor of square root of d times the best approximation. So d here is the number of modes. So in 5 dimensions, this is square root of 5. Okay, so purely using matrix methods, you can get an approximation algorithm. No randomization yet. And this is a little bit expensive because this is n to the power of d plus 1. N is the size of each mode, and d is the total number of modes. So this n to the power of d plus 1. You can see that this is really, really expensive. So I won't have too much time to talk about my work, but basically, since this cost is so high, we've worked on methods to reduce this cost. And so maybe I'll just talk about one of these methods. So in this paper that came out about a couple of years ago, we developed several algorithms that extended this sequentially truncated algorithm. So we developed a randomized version of it. We developed an adaptive version of it, something known as the structure preserving version of it. The first one, the algorithm already existed. So what we did here was we proved theorems related to the accuracy of the randomized algorithms here. And we developed analysis for this. So since I'm short of time, let me just talk about one of them. Well, actually, it's not too hard. What you do is basically, instead of every time you see the SVD, you replace it by the randomized SVD. Okay, so that's the first algorithm is basically that. Okay, you take the SVD every time you see an SVD, just replace it with a randomized SVD. What's challenging about it is to work out the computational cost and the analysis of it. So you get this low rank approximation. It looks a lot very similar. The only difference is that you're using the randomized SVD instead of the SVD. Okay, so I'll just show you how it works. So here's a 25 by 25 by 25 by 25 by 25 tensor. This is known as it's like the Hilbert matrix, if you know about it. I chose the oversampling parameter 5. This has 9 million non-zeros. So even though the dimension per mode is small, the matrix, the tensor size can be large. This is the algorithm sequentially truncated. This is the algorithm that already existed, sequentially truncated. And the randomized algorithm is actually doing pretty well. It's actually even beating this. Remember, this is not the best possible algorithm, so we're allowed to beat it here. So it's doing really well. And we get about a factor of 5 speed up, or maybe lesser. Yeah, maybe factor of 4 speed up compared to the standard algorithm. This is a pretty small tensor. For larger tensors, we are able to get better speeds. And then I told you that we work on the analysis. So we developed bounds. I won't go into what these bounds are, but we're able to develop analysis for it. And here our bounds are pretty good. So this is one realization of the randomized algorithm, and this is the bound and expectation, and it's matching pretty well. Okay, so then we developed an algorithm when we don't know the rank a priori, but we just wanted a low rank approximation. That's the adaptive version. And then we developed a version that's we call it structure preserving, and we call it structure preserving because it preserved the properties of the core tensor in a special way. So if the entries of the original matrix are sparse, this is going to be sparse. If this is positive or integer valued, you want your decomposition to preserve those properties. So this core tensor will have those properties. So that's why we call it structure preserving. So it's a really fun algorithm to come up with. We haven't found super application for it, but at least we can show that it's much cheaper to compute this approximation. So I won't go too much into it, but that was a really nice idea that we came up with, if I can say so myself. So it worked very well on big data sets. So we were able to run it on problems as gigantic as this. So you look at these numbers, these are gigantic problems. And even without using high performance computing, we were able to run it on standard desktops, whereas standard methods just wouldn't be able to run it on these kinds of problems. So when the algorithms that I talked about for the Tucker, they kind of work very well in 3 to 5 dimensions. But when you get into 10 or 15 dimensions, even 100 to the power of 15 is a huge number. So there is a different flavor of tensors known as a tensor train decomposition, and it's a really hard. It's an entire talk on itself, but we developed randomized algorithms for this tensor train decompositions as well. So that's some work that just came. We just submitted last year, 2021. Yeah, I just want to point out that there's no one way of looking at tensors, and like I said, there are 7 or 8 different ways of looking at tensors. So there's a lot of opportunity. Like I said, if you're starting out in this area, looking for a PhD topic, this is a fantastic topic, in my opinion. So we developed these 3 algorithms and analysis for them. And more than the algorithms are really hard to understand, but we have code available, so you can apply it with your data set. If you're interested in following up, these are the papers that we're based on. And thank you very much again for your attention. I'm sorry if I went over time.